Ladies and gentlemen, here I'm presenting to you a historic landmark resembling a lighthouse. It was built in 1924 and originally hid a water tower with tank and plumbing, which were decommissioned in 1931, subsequently dismantled, while the shell remained, was purchased in 1958 by the city, underwent several restorations, and you probably guessed it by now, we were asked to look at it because of moisture related problems. This tower is approximately 120 foot tall and could be roughly divided into a base, stem and the lantern portion at the very top. The base is square, approximately 30 foot by 30 foot. The base and the stem are built with the reinforced concrete structure. Base is filled with concrete masonry, while the stem is filled with frame panels covered with stucco. The top lantern is split into two levels. The base, which is hexagonal in plan, just like stem, but made of steel studs covered with plaster. And the top one is formed by a large glass dome, which is by itself topped with a small lantern. The dome consists of curved glued laminated timber rafters and beams, which is called glulam, covered with copper sheet metal profiles soldered together and filled with wired clear glass panels structurally sealed to the copper, forming altogether a bespoke sloped glazing assembly. The base of the dome is also made of copper sheet metal, forming a water table transitioning from the round plan of the sloped glazing to the hexagonal plan of the walls below. All walls of this tower are tilted inward, and all those levels are separated by composite floor slabs. It could be said that this building does not have a roof on its own. The entire footprint is covered by the inwardly tilted walls, fragments of terraces that cover interior spaces, and the slopy glazing at the top. You can see that the ground level is enclosed with concrete masonry walls with exterior wooden doors and windows. The windows are fixed and contain both glazed sections and sections that are permanently opened for ventilation with louvers located directly above the ground. The walls are flash plastered with textured cementitious stucco only outside and painted both inside and outside. And the perimeter walls located in this upper part of the base are tilted inwards approximately 4 degrees and unfortunately receive water discharge from the upper portion of the tower. The base of the tower is the only portion that actually has its own function besides purely aesthetic landmark. It is used by the city for storage, and this function required weather protection. The stem of the tower has an octagonal plan. Its exterior walls are tilted inwardly approximately 3 degrees from plumb and consist of the miscellaneous panels that we are going to describe later, which are installed flush with the concrete structure and stucco together with textured stucco. Those panels include fixed wooden windows. So 3 degrees may not sound like much, but because this part, the stem, is almost 70 foot tall, that inward tilt covers approximately 20% of the building's footprint. Above the top terrace we see what in a normal lighthouse would be a lantern room with a perimeter gallery, except that the walls are not fully glazed. They are also inwardly tilted approximately 2 degrees, and there is a small octagonal room inside of it. allowing ample access to the exterior perimeter. This top level was completely rebuilt in 1990s with a new steel structure supporting a new composite concrete floor slabs, replacing the previous deteriorated wooden assemblies. And on top of this slab, a light gauge galvanized steel studwork supports the exterior walls and the top slab with a dome above it. Exterior walls are covered with a cement board sheeting with a cementitious stucco applied on exterior faces, and these walls are punched with 16 openings, including 4 wooden doors facing the cardinal directions and 4 wooden windows facing ordinal directions. In addition to these openings, later modifications added 8 vents. The openings louvered with connections to a large exhaust fan, and they actually work in the opposite mode. They are sucking air from outside and push it inside. The upper level of the lantern, which consists of the glazed dome and the small blue lantern, were also completely rebuilt during the same renovation in the 1990s, just as the level below. It consists of a light gauge steel structure supporting a composite concrete floor slab on which that wooden dome structure is anchored. The walls of the top terrace support the floor slab perimeter of the dome, and there is a small 2 feet and a half by 2 feet and a half opening through which a portable ladder is fitted. The dome structure is made of glue lump cage consisting of concentric curved ribs and horizontal rails, also made of glue lump. And those members are clad with bent copper profiles soldered together, nailed onto the glue lump and glazed with a wired single clear glass sealed into those rectangular openings with the silicone sealant. You can see that the top of the dome structure is bonded into a steel ring onto which a decorative copper-clad and capped lantern is attached, glazed with blue single glass. There is no ventilation of either the dome or the top blue lantern, and the slope glazing does not have any secondary or tertiary drainage. So what is wrong with this building? We were not aware of any specific weather or flood-proofing criteria. This is a historic building which needs to be just fit for its use. In this case, there are 2 functions. One is the storage structure for outdoor building materials and outdoor seasonal decorations, which may require some dry conditions. And the second was purely aesthetic, as a monument, as a landmark. Obviously there was a concern about observed deterioration of structural components of the tower itself that were exposed to moisture. But the challenge here is that this building was never intended to be waterproof. Quite to the contrary. Anyway, in our review I focused on the following criteria. Primarily it's the weather resistance, second it's the aesthetics, durability of course, airtightness and wildlife resistance. An obvious challenge in this case is the inward tilt of all walls combined with a lack of any weather resistant layers. There are a few materials like that silicone sealant and the copper that did not show almost any deterioration. Here we don't see any patina on the copper, which simply is a testament to the very clean air in this part of the country. while other materials such as wood and steel were observed at different levels of deterioration, including quite severe. Night footage emphasizes the bulging and spalling of the stucco, and the thermal images taken in the morning show the thermal decoupling particularly visible along the beams. Bulging and spalling of the stucco combined with the observations inside, about which we'll talk in a moment, prompted the city to fence off the area for safety. The stem of the tower is built with the reinforced cast-in-place concrete cage, forming rectangular openings that are filled with lightweight panels. And there are 7 varieties of these panels that we found inside. Starting with the original one, which is just a wooden frame made of nailed 2x4s with lath and the stucco applied directly to them, and then 6 different types of repairs that were subsequently produced throughout the history of this tower. None of the repairs address the issues of the movement joints nor the weather resistance. Yes, this is daylight visible through the joints. So I am going to perform 15 water tests following a modified procedure ASTM E1105 by raising that water rack every 15 minutes. It's 8 o'clock in the morning. We are preparing for water testing. This is the north wall of the tower's stem, and the day is so far windless, and so reported by the Miami airport station. The water is on, and the spray rack starts spraying. This very first test produced 6 leaks, and 4 of them were located in a base below the terrace. They were coming through the fenestrations as well as through the wall itself, which is very badly cracked. It doesn't help that the terrace doesn't have any waterproofing, nor there is any flashing at the base of the wall above. And the stucco is so badly cracked that it just leaks through. This is the test number 1, just below the sill of the first keyhole window. And we are getting ready to move this rack upwards and begin the second stage of testing. The testing starts at the second testing site, which is the first keyhole window on the north elevation. The second test produced only 3 water leaks from the window and its surroundings. As you can see here, they are fairly severe. 10 minutes later, the testing still in progress. There are numerous leaks observed inside. Test number 3 produced 5 leaks, mostly through the stucco and this window and its surroundings. Those 15 water spray tests that I conducted on those 2 walls produced a total of 70 leaks, 70. So we wouldn't be able to go into detail of each of them. but most of them are typical in scope. They went through the windows and they went through the stucco. The third testing site above the head of the keyhole window on the north side. Some of those leaks, as you can see, go directly through the stucco. Just an illustration of a well-known fact that stucco by itself does not provide much of weather resistance. You can see the creative way in which the framing was repaired from behind. We are finishing the test number 3 on the north elevation, just above the keyhole window. Test number 4, just above the seal of the blanked keyhole window. The 2x4s were replaced with new ones that had the metal lath nailed to the front of them, and then they were grouted together with the back of the existing stucco. It's no longer quiet inside. That sound of water droplets reverberating through the empty shell is pretty overwhelming. You can see the light through at the transitions around the openings. A little bit after 9:30, north elevation. The test number 4 just finished. We are going to move it higher. And this test number 5. And this is test number 5, just at the seal of the second keyhole window, the second existing one. Those 90-degree connections between the vertical studs and the 2x6s nailed to the adjacent concrete are very weak connections with toenails, with fasteners acting as bending. This is the end of the test 5, around 9:47 a.m. We're going to move it over the second keyhole window. Test number 6, it's 9:50 a.m. Most of those studs are cut slightly too short, and therefore the whole lateral resistance relies on bending of 2 nails. And some ends of those studs simply rot away, leaving a gap even bigger, even less supported. 10 o'clock, still continuing with the testing. Here's the test number 7. This one is right below the terrace, but still below the top keyhole window. We are finishing number 7, the test number 7, in front of the bottom plywood panel. Now this panel replacement ironically has some asphalt membrane behind it, but it wasn't transitioned properly. And here is number 8. This is 10:24. We just began test number 8 at the top on the north elevation. So here are we just below the overhang of the top terrace, which normally should provide some protection from elements, but this terrace also doesn't have any dedicated weatherproofing, nor it has any flashing at the base of the wall above. But it seems primarily that it's the elevation and the exposure that exposes it to the wind-driven rain. We are re-rigging the rack to the windward side. This is Thursday afternoon. We are on the southeast side of the tower, preparing for the test number 9. This is the wall We're going to test. It's a windward wall. That's why it was picked up. And the test started. It's 1:45 p.m. What we see here is a leak going through the base of the wall above and through the terrace slab, because there is neither any base wall flashing nor any waterproofing on the slab. So it just goes down to the base, and that's where it drips. Finishing the test number 9. It's approximately 2 o'clock, and the only leaks that were found are below the deck, indicating that the leakage happens along the base of the wall. And here it is, test number 10. So it's interesting to see some of those newest panels with cementitious board still leaking. They don't leak much through the field, they leak at the connections, which were never addressed properly. You can see the light through some of them. And that leakage is pretty abundant. We are using wind door advantage to pressurize this wall, and also it causes lots of water splash on adjacent panels, which leak profusely right now. Another 15 minutes passed. We are going to move the spray rack higher. It's currently 15 past 2. And this is our test number 11. So the test number 11 produced only 4 leaks, but we already have 50 leaks. Some of them are still discharging water inside, so that dripping noise becomes quite overwhelming inside. We can see quite a lot of history on these walls, the traces of previous repairs, most likely after some hurricanes or windstorms. On this wall, most leaks come through the joints, the perimeter joints of the panels and the perimeter joints of windows within those panels. You can see jumps and heads listed on that report page. Finishing test number 11, and we'll be rigging test number 12. There it is, test number 12. So here again, as we go higher, one would expect to see less evidence of water damage, because there should be theoretically some protection offered by that top terrace. But again, like with the previous set of tests, this is not confirmed. This top terrace leaks just as everything else. This is number 13, the test number 13. We just moved it from the previous position 12. It's 2:47 p.m. So an interesting thing started to happen. We get some delayed leaks starting dripping inside from those masonry walls at the bottom, and the sound of dripping after 60 leaks becomes quite stunning inside. So it's interesting to see that it takes approximately 2 hours of water testing on this wall for some leaks to start dripping on the inner side. 14th test. It's currently 5 past
free.
One of the interesting and peculiar things about those panels is that you can see that those are horizontal 2x6s, approximately at quarter points of the panels, are placed vertically. They are located in its weaker axis toward the lateral load, so they would actually be bent in its weaker axis by wind load. You can see one of the many different repair versions, this one with the plywood, and behind the plywood there is an asphalt paper and a stucco on a metal lath. Nevertheless, they were terminated around the panel perimeter, so it just looks just the same.
This is the 15th test at the very top. It's 3:20 Thursday.
Here we can see some exceptions, namely there are fastener holes, or the tips of the fasteners, that are showing some water going through. Those fasteners penetrate the membrane. There are holes in that wooden siding, letting the wildlife in, so you could see some eggs, some nesting inside. The inward tilt of walls is not just a challenge because it's more exposed to elements due to the gravity, but also it means that when top starts leaking, it drips toward the center of the building, making it very difficult to contain, drain and discharge the leaks inside, which was one of the options that we considered at the very beginning, just adding internal flushing gutters and downspouts.
This is 3:40 Thursday afternoon. We are done with the southeast side.
And here's some interesting footage we cut later. There is discharge from behind the stucco in front of the wall long after we finished the testing. In the meantime, I also water spray tested the base of the dome.
Here is the setup for the 5012 EMA testing. This is the famous Monarch nozzle with the gauge. The gauge shows pretty good pressure. We are testing the base of the tower where the stucco meets the flashing. This is 11:45, so we need to spray for 5 minutes.
And here we can see the results. The interior of the dome is perfectly dry except for the base of it, where that water table flashing failed dramatically. Here we can see only part of it. A majority of water actually ended inside that octagonal room below. You can see it here. It's really hard to distinguish whether it actually went through the wall at this level or through the flashing below and transferred inside. These results proved to be inconsistent with the heavy water damage observed on the glulam structure of the dome. I took this thermal image in the morning one day that shows the lowest temperature at the dome is approximately 45 degrees Fahrenheit. I climbed inside and I measured that the interior dew point inside the dome was approximately 67 degrees at the time, which explained why there was water condensation rolling down the glass and dripping over the seals. So I installed a long-term monitoring to figure out this and other phenomena. Namely, why a tall tower like that would not dry itself by the sheer power of the stack effect. Previously I measured the differential pressures and the air speeds at different locations, and none of it made much sense. There should be a strong upward draft, but it seemed to be somehow suppressed. So a couple of weeks later we got our first results. It turned out that there was something very strange going on in this dome. You may remember I said this is a very unusual configuration for a normal lighthouse. The combination of temperature and humidity inside is simply oppressive, and you may remember me saying there is no vent at the top of the dome, at the blue lantern, nothing that would vent it out. There is this huge fan working around the clock at the lantern room, which is pushing air from outside inside the room in an empty tower. So apparently there was some concerned effort in the past in order to counteract this strange suppressed air movement and produced some ventilation at the top level. There are 7 temperature sensors and 6 humidity sensors logging the data, and after analyzing it I was able to produce a chart like that. The horizontal axis is time, the vertical axis is temperature, and those lines represent temperatures and dew points. When temperature and dew point cross, it means that we have condensing conditions, and for convenience I marked them with blue color. I also drew correlations between the weather events, between our water testing and the temperatures observed outside. So now, after all this work is done, how do we interpret this chart and how do we interpret these findings? On the left side you can see a sketch of a passive solar tower in a hot climate, which pulls air at the bottom and discharges at the top. And this is contrasted with the tower shown on the right side of the sketch, which is our tower. Regardless whether the fan is operating or not, the air inside is pretty much stagnant because it's capped at the top with a very hot air generated by that small greenhouse, and this air doesn't have anywhere to go. And why do we care? Because the updraft of air would dry the interior of the tower to the level seen outside, which means in this case of an incredibly leaky tower that it would happily dry it out. It doesn't work this way, unfortunately. There are other things that I investigated, including the challenges that this tower experienced with the discoloration of its coating. I even went so far as to visit the manufacturing facility of the paint in question. But this is a tangent that I don't believe we really need to go through. This video is already over half an hour long. I'm sure if you are interested in going on those tangents, you would let me know and I would just add that material. What you see here is a small fraction of the materials I collected on this project. So what did I accomplish so far? Through some incredibly meticulous water testing, I proved that the tower that was never intended to be weather resistant leaks water like a sieve. Not much surprise here. There are some fairly obvious observations, for example that wooden windows, poorly made and installed in inwardly tilted walls with the seals that actually provide a pocket for water to submerge those conditions, would rot sooner rather than later, and they did indeed. So now the next question is obvious one. How do we fix it? There are structural items such as the primary structure of the base of the lantern and the secondary structure of the panels in the stem that are not only dangerous but also urgent. But they were outside of my scope. My scope was the weather resistance. There are some items that are fairly obvious, such as the traffic resistant waterproofing coating on the terraces and the base flashing. There are several different options for repairs of the stem, and those overlap with structural considerations. We could either clad over the concrete structure or keep the existing configuration of panels, doubling essentially the number of the visible movement joints. And there could be different approaches to layering of those panels. We can also venture into one more engineering discipline. On the mechanical side, we can either reconfigure the ducts in the serving the existing fan or just add the vent at the top in order to assure the proper circulation of air inside the tower. I certainly hope that I'll be able to follow with the description of the actual repairs and measurements taken after the repairs and replacements were implemented, because it's the results that matter after all. Thank you, and I hope you enjoyed this video. As always, if you like what you see, please consider donating to our cause, which is research and education in building enclosures. Bye!